Hello, everybody. Welcome to the Ultromics industry-sponsored session. Today, we're going to talk about AI-based diagnostics for echocardiography. My name's Ross. I'm founder of Ultromics, and we've got three wonderful speakers today who are going to talk about their experience using the Ultromics AI diagnostics. We have two in particular we're going to discuss today. The first is a diagnostic algorithm for HFpEF, and the second is one for cardiac amyloidosis. Both modules are FDA cleared, and there's now reimbursement available for both modules as well. We're going to hear about the validation that's gone into both modules, the real-world clinical implementation of these models, and how they're changing the clinical practice. We are going to hear from three speakers today. Dr. Pelliker, who's going to discuss the validation of the models. We're going to hear from Dr. Slivnik, who's going to discuss the clinical implementation and validation within his echo lab of the models. And we're going to hear from Dr. Jamal on the clinical implementation within his cardio-oncology center. So without further ado, I'd like to invite Dr. Patricia Pelliker to speak about her talk on AI for HFpEF and amyloidosis. Thanks, Patty.
Thanks, Ross. Hello, everyone. It's my pleasure to talk about this really exciting topic. This is the overall objectives for this session: to understand our progress in detection of HFpEF and amyloid cardiomyopathy with AI echo, to appreciate the comparison of the AI models with current clinical models for detection, and to learn about the implementation of AI echo models for disease detection in your clinical workflows. Let me take you back to 2019. AI and echo was pretty new there. At that time, there wasn't a lot going on. And I wanted to build a model to develop something that would be really impactful. And therefore, the idea was to build a model to detect HFpEF. Certainly, assessment of diastolic dysfunction is a challenge for echocardiography, and HFpEF is a huge public health problem, and it's challenging to detect. I received a grant from the American Society of Echocardiography Foundation for this work and identified Ultromics as a partner to work with. This has been a great partnership. So if you think about it, there's really a lot of information within this apical four-chamber view. And we wondered if you could detect HFpEF just from this limited bit of information. Two different patients, obviously. And you can appreciate left ventricular function, left atrial size, motion of the mitral and tricuspid annulus, wall thicknesses, a lot of information that we don't really necessarily evaluate thoroughly. So we worked on developing this model. Our control population was nearly 4,000 patients without heart failure, and that is without heart failure for even a year after their echo, with normal ejection fraction, with normal or grade 1 diastolic dysfunction, and the HFpEF population was nearly 3,000 patients with a clinical diagnosis of heart failure, preserved ejection fraction, and elevated filling pressure by echo. We withheld 17% for validation. This illustrates the model development. Data came from multiple ultrasound systems in our practice. We examined sequences of 30 frames. Each frame was resized to 256 by 256 pixels, and data augmentation was randomly applied, including flipping this image in different directions and also changing gains and other augmentations. This shows the model and the model output. yielded information either the suggestive of HFpEF, not suggestive, or uncertain. This AI echo model had excellent discrimination and classification. Shown here is the AUROC for training, validation, and testing. The testing was performed in a separate population, a different Mayo Clinic site, where the data had not been used for training. Similar numbers of controls and HFpEF patients. Patients were matched for sex, year of echo, and we tried to match as well as we could for age, although the HFpEF patients were a bit older. So this was echoes done by different sonographers and interpreted by different physicians. Our model yielded an uncertainty of about 7%. The AUROC in testing was 0.91, sensitivity 88%, specificity 82%, and positive and negative predictive values are shown. Of course, we want to make sure that this is really assessing something meaningful, and therefore we looked at age-adjusted risk of mortality and its relationship to the output with the AI echo model. And you can see that the survival was worse in patients with HFpEF compared to those without, and intermediate in those with uncertain classification. Another thing we wanted to evaluate was how the model performed compared to standard clinical models used for detecting HFpEF. The two standard clinical models most widely used are the HFpEF model, which uses these variables, quite a number of variables, and the more simple H2FpEF model, which uses these variables. A problem with both of these models is that they yield a lot of indeterminate results, indeterminate for whether HFpEF is present. And fortunately, our AI echo model was able to reclassify 75% of these indeterminates, yielding a diagnostic result. Back to this example, which one has HFpEF? Well, this first example was a 53-year-old woman with a murmur, and the model yielded a very low score, no HFpEF, with good confidence. On the other hand, this is a 56-year-old woman with dyspnea and acute on chronic HFpEF, a high score, good confidence in interpretation. We also wanted to know if our model was able to identify patients at risk for heart failure hospitalization and cardiac mortality. And indeed, the model performed well. This was a separate study using a second version of the model. We used the National Death Index to determine the cause of death, and the data were adjudicated independently of the AI assessment. We also classified according to the output score, and this is heart failure hospitalization by the quartile of score. So these are the results for heart failure hospitalization, with heart failure hospitalization being more in those with the positive result. This was the same for cardiac mortality, and the AI model was superior to the clinical scores. External validation of an AI echo model is very important, and this is work that was done by Dr. Jordi Strom and colleagues at Beth Israel Deaconess, evaluating the model in patients with HFpEF and controls. They noted that classification was higher for AI echo compared to clinical scores. Discrimination was similar to the H2FpEF score, but the combined clinical score and AI echo was the best solution for identifying patients for appropriate treatment. An acid test for an AI echo model is to see how it performs with a completely different ultrasound system. And for this, we chose to use point of care, this tablet device, and compared it with the apical four-chamber view from a full echo using a different vendor. You can see that the AI prediction score is compared here. It's not perfect, but it's pretty good. And for those in which both the transthoracic echo and handheld were positive by the AI analysis, they had the higher clinical score, and those in which they're both negative had the lower clinical score. Our next problem that we wanted to tackle was whether we could build an AI echo model to detect cardiac amyloidosis. This is certainly a huge challenge in our clinical practice and a very important diagnosis to make, considering that treatments are now available and most effective early in the course of disease. We examined the prevalence of cardiac amyloidosis in patients undergoing echocardiography in our clinical practice. This was 1 year's worth of echocardiograms at Mayo Clinic in Rochester. 1.25% had cardiac amyloidosis. The percentage increased with age. You can see the ATTRs are shown in orange. But interestingly, there was about 0.5% in which those echo images suggested possible cardiac amyloidosis, but the diagnosis was not pursued. This is really an opportunity for an AI model. The AI model that was built with Ultromix has been compared with other models that are available, including the HUDO model, which is based on medical claims and uses a random forest design. The clinical model, Mayo ATTR cardiomyopathy, which uses logistic regression. Dr. Ouyang's EchoNet LVH, ResNet 3D model, and then here's our results for EchoGo amyloidosis with a very good AUC. These deep learning models were clearly better, and also it was shown that there was a low risk of harms from racial bias. We are extremely excited about the work that we have done developing this model for detection of cardiac amyloid, and I'm going to turn this over to Dr. Jeremy Slivnik, who's going to tell you about the paper and the work that is underpinning the paper that we recently published in European Heart Journal. And thank you for your attention.
Thank you, Patty, for that excellent talk. I think one of the things that stands out for me in the EchoGo heart failure data is the remarkable consistency with which it is able to predict heart failure hospitalization between two completely different cohorts. The risk prediction was nearly threefold increased risk of heart failure hospitalization, I think showing the benefits of robust validation and the work we've done with Dr. Pellicker. With that said, I think that was a very nice tee up for Dr. Slivnik's presentation, so I'd like to welcome him to the stage to talk about AI for cardiac amyloidosis detection.
Hi, thank you very much. I'm very pleased to have the opportunity to be here to speak with you about our study. Here are my disclosures. So I think as Patty excellently illustrated, we've seen really a major change in the paradigm of transthyretin cardiac amyloidosis. This started as a disease that was universally fatal within 3 to 4 years, as we can see in the placebo arm of ATTR ACT, to a disease where patients, over 80% of patients can live longer than 4 years. And this is due to the influx of treatments that have drastically changed the natural history of this disease. However, we know that patients can be diagnosed along a spectrum of disease severity, ranging from preclinical disease, in which, although we're studying this actively, we don't know whether treatments are beneficial, or patients that can present too late with late-stage disease and an NYHA Class 4 or a NAC Stage 3, at which point therapies are unlikely to be beneficial. And there's really a window of time where we need to pick up these patients. And it's really critical that we be able to leverage echocardiography to its fullest extent to be able to screen for these people at the right time. As we know, echocardiography is really a frontline screening tool for cardiac amyloidosis. Again, patients come in often with undifferentiated symptoms, and echo is one of the first tests that's typically ordered in this population. Yet, we know there's increasing understanding that single parameters alone, even apical sparing, may lack adequate accuracy to screen patients effectively, and that multi-parametric models, although they may improve accuracy, are time-consuming to calculate and difficult to implement in busy echocardiography labs. AI, therefore, offers a potential scalable solution to underdiagnosis of this treatable and not-so-rare condition. Yet, we talk a lot about the potential benefits of artificial intelligence, but I think it's important to understand the potential limitations. AI is only as good as what we train it to do, and only as good as how rigorous our ground truth is. Models may be trained without adequate external validation, and as Patty alluded to, sociodemographic bias in the cohorts can also be harmful when deployed in clinical practice in populations that these have not been studied in. Homogeneous research teams and a lack of comparison to the standard of care can also limit the potential generalizability. So to address this, potential ways to do this are robust labeling of data based on guideline definitions of cardiac amyloidosis, the leveraging of large validation cohorts, and the use of diverse multi-ethnic populations to ensure that these models are generalizable to the patients that all of us see in clinic. And additionally, it's important to involve stakeholders from key different areas who bring different expertise to the table, and that we validate these against the existing standard of care. So the overall design of this study involved basically 3 sites for training of this model, and the model was ultimately tested and validated at 18 sites. The model was developed utilizing data from the Mayo Clinic, and this is highly phenotyped, rigorous data trained against the ground truth definition of cardiac amyloidosis from the guidelines, either endomyocardial biopsy, extracardiac biopsy with typical imaging features in the case of AL cardiomyopathy, or non-invasively with negative comprehensive light chain evaluation and positive PYP. Once developed, the model was then tested and validated in a diverse global multi-ethnic population spanning 4 countries and 18 academic medical centers. As you can see, this really involved a village of people, including AI support team, programmers, heart failure cardiologists, cardiac imagers. A lot of stakeholders from the various aspects of cardiac amyloid care were involved in the creation of this. Similar to the AI HFpEF model, we trained these utilizing an apical 4-chamber view, which was automatically detected from the echocardiogram, and was trained to detect cardiac amyloidosis and differentiating it from typical hypertrophic phenotypes that we're often encountering in clinical practice, such as HCM, aortic stenosis, hypertensive LVH, HFpEF, as well as MGUS, which is often on the differential as well when we're looking for AL disease. The model was then developed utilizing this cohort from the Mayo Clinic, and then externally validated utilizing the global multi-ethnic population. As we can see, this is the performance of the model within the entire cohort. We can see that it performs very robustly with an AUC of 0.93, sensitivity of 85%, and specificity of 93%. We also wanted to look at this in really sort of a stress test situation. So we took patients within the cohort, the subgroup of patients that were actually clinically suspected to have cardiac amyloid and were either confirmed or found not to have the disease by PYP. So this was basically a heart failure referral population. These patients were sick, and they were patients that the clinician suspected to have disease. And we can see that the performance remains high even in this population. And even when the controls were matched based on age, gender, and wall thickness, we can see that performance remains high. We then sought to compare this to the current standard of care, and you can see that the 2 common multi-parametric risk scores that are used in clinical practice, the IWT and the TCAS score, are superimposed on the on the AI model for amyloid detection. And we found that there was superior performance for the AI model as compared to both of these scores. And we can also model the potential positive predictive value across the prevalences that we're likely to encounter in clinical practice. And in general, we think about 5 to 15% as sort of that magic area where we're going to want to, where we have high concern for amyloid. And we can see that across these prevalences, the AI model maintains robust performance. As Dr. Pellica presented, this was also additionally externally validated at another center and found to have similar results, again, reinforcing the generalizability of these findings. So talking about this in conclusion, the AI for cardiac amyloidosis is potentially a rapid, automated, and accurate solution to detect cardiac amyloid. One of the nice things about it is it runs from a single apical 4-chamber view, meaning that even on limited echoes, we can get an evaluation for cardiac amyloid. And it can also be performed both prospectively or retrospectively at health centers. Certainly, there is need for additional studies, and we do need real-world validation to better understand the accuracy and the user interaction. I think Jamal is going to present some of that data after me. And I think we're still trying to find out what the performance rate is in early-stage disease, but I think this is an area that we really need to study. So based on these results, this model ultimately was FDA and CE mark approved. And now I think we're going to talk a little bit more about how this can be implemented into day-to-day clinical practice. This is sort of one of the concepts that I think is front and center in my mind when I think about deploying models such as this, is what is the pretest probability of the population that we're going to be deploying this in. And often AI models may be trained or validated in disease prevalences that don't mimic clinical practice, something around 50 to 70% enrichment. However, we often plan to deploy these at prevalences that are much lower, and that brings the potential for false positive results. And I think even when you look at this, although we see superior performance of the AI model across all of these prevalences, if you were to roll this out at sort of the general echo screening population, there's a high percentage chance that you're going to see a lot of false positives. And so it's really critical that we find a way to refine pretest probability such that we can really optimize model performance. This is data from Ashley Ackerman and colleagues that showed that we can actually leverage the existing AI HFpEF model to augment the accuracy of the cardiac amyloidosis detection model. This is the table showing that when we look at EchoGo amyloidosis, we have 84% sensitivity and 91% specificity. However, when we integrate that into the positive cases by EchoGo heart failure, we can augment both sensitivity and specificity. And importantly, we raise our negative predictive value. So this highlights the potential of an AI pipeline to screen for HFpEF and then run those cases for cardiac amyloidosis in order to augment the pretest probability. So I'm going to talk a little bit about the workflow that we've integrated or that we've employed for integrating this AI model into our clinical practice. Jamal, I think, will touch much more extensively on sort of the experience at their center, but I at least want to show sort of what we do here. So, essentially now when we have a study where we basically acquire the study by the sonographer, images that are sent to EchoGo are then de-identified and sent into a cloud-based platform, at which point an automated EF assessment is performed utilizing ultraomics technology. Cases that have an EF of greater than 50% are then sent for EchoGo HFpEF analysis, with positive cases then sent on for amyloid analysis to create that pipeline of increased pretest probability. The reports are then re-identified to the patient information, sent into the report, and added as a secondary capture at the end of our DICOM. The Echo reader then receives this, integrates it into their reporting system, and then based on that, we then we contact the referring physicians about the concern for cardiac amyloidosis and provide recommendations either for referral to a specialist in cardiac amyloid or guideline-directed screening recommendations such as PYP, light chain, and light chain analysis. One of the things that we know about this, though, is that we're not making all these decisions solely based on echoes in clinical practice. Our clinicians are integrating red flag features, clinical family history, ECG, and labs, and all of this is being integrated into our pretest probability. And so it's really critical that the physician have the optional override to send cases that they feel are high pretest probability, such that we can potentially augment the screening for these patients in addition to just the HFpEF pipeline. So I'll leave with an example of a patient that we saw at our center where I felt like it really kind of showed me the potential for this technology. This was a 67-year-old male presenting with dyspnea and had multiple pulmonary vein isolations. They have, as you can see, only mildly increased wall thickness and mildly reduced ejection fraction, and they don't meet criteria for conventional apical sparing based on the GLS. However, their CMR ended up being typical for cardiac amyloidosis. And when we went back and looked at this case, we found that this patient was actually positive by the EchoGo heart failure technology. Again, I think highlighting its potential use in clinical practice. And here we can see sort of the typical CMR features that were observed in this case, with increased T1 and extracellular volume as well as diffuse late gadolinium enhancement. So in conclusion, EchoGo amyloidosis provides accurate detection of cardiac amyloid from a single apical 4-chamber view. The application of EchoGo amyloid has the potential to offer a scalable solution to improve detection of cardiac amyloidosis globally. Thank you very much.
Thank you, Jeremy, for that excellent talk. I don't know if I've seen another algorithm so extensively validated across 18 global sites. So that's truly impressive work that yourself and Dr. Pelliker led there, so thank you. We're going to hand over now to Dr. Jamal, who's going to speak about the real-world implementation of EchoGo in his center at City of Hope. Dr. Jamal.
Oops. All right, so we're on the screen. Thank you so much for this opportunity to share our experience. So I'll be talking about implementation of this particular solution of artificial intelligence-based review of echocardiography for diagnosis of cardiac amyloidosis at our cancer center, City of Hope in Los Angeles County. So, the populations that are at risk that we're most concerned with, I think within the cardiology community, we're pretty well aware of the risk of amyloid in the heart failure population as well as in aortic stenosis. So the prevalence rate is pretty well known at about 15% for HFpEF patients having ATTR as the etiology for their heart failure. And we also now understand that about 16% of patients who have aortic stenosis have aortic stenosis as a consequence of mostly wild-type ATTR. What may be less well recognized amongst cardiologists is the prevalence rate of AL amyloidosis in patients who have monoclonal gammopathies. So in the multiple myeloma population, as an example, there's about a 10 to 15% incidence of AL cardiac amyloidosis in myeloma. So when I see an echocardiogram come across in our lab with any of these indications for the study, we're scrutinizing those echoes more closely to see if we see any signs of amyloidosis. Now, the problem with this is that amyloid generally tends to be diagnosed pretty late, and the reason for this is that the red flag clinical symptoms are very nonspecific, and we pride ourselves in echo labs as being the first ones to pick up the disease, but we're picking it up pretty late. It takes a fair amount of disease advancement before you're going to see clear signs on an echocardiogram. Rarely, it becomes a bigger problem in busier clinical practices in the community where there are large volumes of echoes being done and more subtle signs are going to go missed. There are novel parameters such as global longitudinal strain which are being utilized more widely, but not everywhere. They can be very helpful if performed more uniformly. And then even simple measurements such as wall thickness, there can be variability in how that's performed. So everybody kind of sees the wall differently, where they see the endocardium begin and end, and where technologists may place the calipers versus where a reader will place the calipers. And so due to all this variability, measuring these issues, these things becomes more complex. And subtle findings like mild wall thickening, trivial pericardial effusions, and reduced tissue velocities, these kinds of things can get overlooked when the ejection fraction is normal. So at City of Hope, I wanted to institute different measures to try to pick up the disease at an earlier time point. So we've done a couple different projects. So one of the first things we did was, why don't we leverage the EMR itself? We use Epic like a lot of institutions do. And so we instituted an algorithm within Epic to identify every patient that has moderate wall thickening of the left ventricle. So we defined that at 1.4. We said if anybody's got a wall thickness of 1.4 centimeters or greater, we're going to flag those patients and review them. And so we generated a list, and it was several hundred patients long. And lo and behold, this list fell into my lap. So I had to review hundreds of echocardiograms to see if they really had moderate LVH or not. And I would have to tell you that about 10% of these patients actually had moderate LVH. The rest were erroneously measured wall thicknesses. And that's just the real world. The wall thickness is not always measured correctly. And so out of that cohort, those 10% of patients, we identified the ones who already had a known diagnosis. The ones who didn't, we then contacted them and referred them to our clinic to be evaluated. So the total effort here, even though it's simple to just say, we're going to have Epic sift through and find all of these patients who have moderate wall thickening, in reality, to implement that, it takes a lot of effort because then you have to review those cases. So then we moved on and said, okay, what else can we do to identify these patients? And so one of the concepts that we considered was, well, we can look at other echo measures that we're not currently utilizing. Everybody's well aware of global longitudinal strain and the apical sparing pattern. Everybody uses that to look for amyloid. Well, what about the other chambers of the heart? They've got amyloid deposition in them as well. So I thought, okay, look, we're going to systematically measure RV strain, LA strain. So I did a project where I studied 150 people. 50 of them had known cardiac amyloidosis, and I wanted to measure the strain in the RV and the LA in these individuals and compare it to patients who didn't have cardiac involvement. And so I'm not going to go through this whole slide, but essentially this is the number of echo parameters in which you find statistically significant differences in patients who have cardiac amyloidosis versus patients who don't have amyloid. And LA strain is actually quite powerful. I think that you can definitely detect quite a bit of disease within the atrium using this measure. But the purpose of showing this slide is to show you how many different features within an echocardiogram really need to be scrutinized in order to determine that someone may have amyloid. And the problem is that in a busy practice, this can be challenging. So all of these different measures and all these projects that we've done for quality improvement have required a high amount of effort, and it requires clinicians to study a lot of different parameters to diagnose the disease. The methodology has to be consistent, and ultimately the diagnosis remains really complex, it's time-consuming, and it's challenging in a busy practice setting. So this is where artificial intelligence really solves these challenges as a single solution to all these different issues. It essentially does all the seeing for us, all from a 4-chamber view, right? So it's going to see the GLS, but it's also going to see the movement and the function of the left atrium. It's going to look at the function of the right ventricle. It'll look for mild amounts of thickening. It'll look for little effusions. It's going to actually watch the velocity of tissue movement, and it's doing this without Doppler, essentially. So all of this work is being done on an automated basis that really minimizes the amount of effort required from a reader that's going through 50 studies in a day. Imaging review also becomes very systematic and consistent. So I'll tell you that initially this was not something that I was looking to do. My initial interaction with Ultromics was really based upon a desire to reduce inter-reader variability and maximize reproducibility in our reporting of ejection fraction, because we are a cancer center, and the cancer center essentially relies on cardiology to provide accurate reports of left ventricular function so that decisions about chemotherapy, immunotherapy, and transplant can be rendered accordingly. And so for that purpose, I felt like the problem was that there's so much variability. As in every lab, there is variability between readers on how much difference there's going to be in our reporting of EF, like where we see the endocardial borders and how we measure ejection fraction. And a huge issue in cardio-onc is that the definition of cardiotoxicity is a drop in EF of 10% below the lower limit of normal. And if you look at published studies on how much variability exists between echo readers, you will find that the amount of variability in EF that's considered acceptable across the general kind of reading population is 10%. So it's acceptable in a lab to have 10% variation in EF, yet that is the definition of cardiotoxicity. So obviously, in a cardio-oncology center, I couldn't tolerate that level of variation in reads, so I needed to minimize that. So, of course, we work with our faculty and our quarterly reviews to sort of minimize reading differences, but AI is a natural, sort of neutral, objective solution to this issue. So that was our initial approach with Ultromics. We wanted to automate and use AI to measure systolic function. The company then later pivoted into disease identification, which we thought was very novel. And so we started working with them to identify patients with heart failure. And this year, we are now looking at, we've been using the algorithm to identify patients with amyloidosis since January. In terms of instituting this solution, we worked with our IT department and Ultromics to set up echo data anonymization and transmission, just like Jeremy went over. Essentially, this requires setting up a system where you send your DICOM anonymized into a cloud-based platform, and then you get back a report. And then we trained our cardiologists to incorporate these findings into our clinical reports. And at this point, every echo done in our lab is run through Ultromics for analysis for HFpEF. I won't go through all these implementation steps, but I will say probably the biggest hurdles were gaining clearance from information security. Every institution obviously wants there needs to be a maintenance of patient privacy, so these studies have to be anonymized. Other hurdles are, building a business case for this. Institutions need to see that it's not going to be, it needs to be revenue neutral or better. And then ultimately, once we did institute the solution, we wanted to improve turnaround times. So turnaround times in terms of how fast the report comes to us. We don't want to slow down readers. Like when a study gets completed, they open it, they want to start reading it and report the findings. We're not going to wait for a report. So the report needed to show up quickly. So ultimately, this required installation of a DICOM router that specifically sends these studies rapidly, and we get them back quickly. And at this point, it's essentially imperceivable to all of us reading in the lab. So we've been using Ultromics now for 1 year. We went live last August, and in total we've sent about 7,700 studies and got back 7,000 of them that were positive. So the 7,000 had ejection fractions above 50%, and about 9% of those were positive for HFpEF. So that's about the positivity rate that we saw. And obviously, we then, these patients were looked at more carefully clinically to ensure that they were being managed appropriately. We've been using EchoGo amyloidosis since January. So of 346 patients that were identified by Ultromics for having HFpEF, 15 of them were then further identified as having amyloidosis. So that's about a 5% positivity rate within our HFpEF population. And the general reason I believe this to be lower than the general population is because this is a cancer setting. So this is not all comers who come to your general hospital with shortness of breath who may be diagnosed with heart failure. These are patients undergoing various forms of cancer therapies, getting large amounts of volume infusions, and so some of the heart failure is iatrogenic. This has resulted in a change in our workflow. So before, we would have to look at multiple different risk factors, and there was always a lack of clarity regarding which patients should be referred for formal amyloidosis evaluation. At this point, we have this one additional very reliable major risk factor, which is a positive report from EchoGo amyloidosis. So, like I said, in the last 6 months, we've seen 15 positives. We looked at those 15 cases. 10 of them had known cardiac amyloid, so obviously those didn't require any further action. But the 5 other cases were unknown patients. We did not know that they had amyloid. One had already passed away, but the other 4 were then referred to our amyloid clinic for further workup. So the other thing that has happened is that I'm starting to see more referrals from divisional colleagues for suspected cardiac amyloid because of the AI analysis. So it used to be that, okay, somebody would see a heart that looks like it might have amyloid, but now I'm getting referrals from colleagues who are saying, I don't really see anything, but the algorithm is reporting amyloidosis. So this is kind of a new and exciting sort of arena because we want to see, is it really detecting amyloidosis earlier than those of us who are specifically looking for it? So that's going to be something we'll have to stay tuned for to see what kind of results we're getting, how many of these patients truly have the disease on evaluation. One other change that we've made is that we're getting a quarterly report from Ultromics for all the positive cases. So once we get that report, I'm reviewing them to see which ones already have known disease. The ones who don't have known disease, we're then referring them to our amyloidosis clinic to be evaluated first for light chain disease, and if they're negative for light chain disease, then we're proceeding with a PYP scan. So the impact of this, I think, is pretty significant, given that approximately 15% of HFpEF and 16% of aortic stenosis is due to ATTR. So this disease is prevalent right now in a really high volume, and it's under-recognized. I think there's a lot of debate right now on how do you identify these patients. So if you read 100 echoes and say that there are 100 patients who have heart failure, how do you find out which of those 15 have ATTR? Are we going to perform cardiac MRIs on all 100 of these heart failure cases? Are we going to do SPEP, UPEP, free light chain evaluations on all of these patients? Are we going to do PYP scans on all these patients? So right now, that is something that is being discussed. One easy solution here is, this is where AI can fit very nicely because we already have echoes on everybody. So if AI can identify those 15 patients for us, it's going to dramatically change the overall morbidity and mortality of ATTR. So right now, I think the biggest thing is to systematically evaluate all these echoes. And if we can do that, I think it'll allow for earlier medical intervention. As the technology sort of advances, I think sensitivity, specificity, and positive predictive values are going to get better and better. And adoption of this AI for these purposes will ultimately improve outcomes and survival. Thank you.
Thank you, Dr. Jamal. One of those rare talks where we actually get to discuss implementation of AI and AI being used in the real world. That was a fantastic talk. So we do have time for some questions. So if there's any questions in the audience, please feel free to come forward to the mic and ask our panel any questions you may have.
Hello. This is really pretty cool. What's it cost? I mean, and how have you factored out, you got to deal with administrators, right? Yeah. So, I mean, we're all suffering. So how do you finance, what's the pro forma like? And what does it cost to send a study?
So I can't speak to exact numbers, but I can tell you, you're absolutely right. We all have to deal with administrators. And I wasn't going to get a whole lot of support for anything without presenting a solid business case. And especially being a cardiologist in a cancer center, the problem is we're not at the top of the food chain. So the hematologists and oncologists generally get what they want, or at least we feel that way. And I have to fight tooth and nail for different advances in cardiology. And so luckily, right now at least, there is support from CMS for reducing heart failure hospitalizations. Everybody is familiar with that. And there is also support from CMS for increasing adoption of novel technologies in medicine. And so as a consequence of this, there is reasonable reimbursement from Medicare for using AI in echocardiography, especially if you identify heart failure, because that will ultimately reduce readmissions. So that's how we were able to essentially we modeled out that this would be revenue at least neutral, perhaps positive. So the hospital may be making some money off of utilizing this. So it's sort of a win-win, we believe. But I'm not the business guy, so I don't have all the numbers.
I can speak to the reimbursement a little bit. So, we were lucky enough, and we decided to go through the hard yards of obtaining a reimbursement code for this technology. I think you've seen it in other areas, like cardiac CT, for FFRCT. There's that reimbursement model. We decided to kind of follow that same approach, and we were fortunate enough to receive a reimbursement code a year or so ago, and thankfully it's receiving very favorable coverage, as Dr. Jamal alluded to. And so we're happy to speak about that more if you'd like to find out after the session.
Well, this is exciting technology, but like a lot of exciting technologies, they are vulnerable to the principle of garbage in, garbage out. So I have two questions related to that principle. First, there are certain patients who, although I agree the apical four-chamber view may be where all four chambers are there, we can see the left atrium, and their best windows may be the parasternal long or whatever. I mean, what happened in those cases? And a second question, since do we include the GLS strain with a baseline, and is there like a specific guideline if you want to adopt that protocol? What has the image that you submit need to include in order to be eligible for that technology?
Yeah, perhaps I could talk to the first question, great questions, and maybe invite Dr. Pellicer to speak a comment further. I think we picked the apical four-chamber view specific. I know there's lots of other views you could select, and indeed adding more views in often makes the model have better discrimination. When you put this out in the real world, often not all the views are available in a busy echo clinic. So it was really kind of a discussion and decision between Dr. Pellicer and myself and my team to decide to pick a single view because we felt that it was the most scalable way of getting this technology out there. And if we could do this, it was a bit of a moonshot with HFpEF. We didn't know whether it was achievable to get a high sensitivity and specificity from a single view for HFpEF. But when we realized we could do it, we felt that it was a better choice to stick with that single view, because then you can scale it not only within hospital systems, but also with a view to sort of POCUS and the communities, which is, I think, some of the data that Dr. Pellicer presented. And Patty, I'm not sure if you want to add to
I would just add that in building the model, we didn't select pretty four-chamber views. This was all four-chamber views. And in looking at some retrospectively, I'm surprised that the AI could make any sense of it. Some of them are just plain homely. But nevertheless, it worked. I think the model doesn't work, though, if you don't have any four-chamber view.
Correct. Yeah, on average, so we've processed nearly over 300,000 studies across the US now, and on average, we are able to process about 93% of them. So 7% of the time we're sort of uncertain, but 93%
And as far as the
go through the
strain,
model.
is it part of the baseline data? And is there a difference that you noticed in those studies that included versus did not include strain, if it's not part of the requisite?
So no, we do not include any measurements in the model. It works purely on pixels only across at least one video clip of one heart cycle of an apical four-chamber view.
Hello, thank you for your talk. I have a couple questions. One, it's do you have data in relation to the area under the curve, the ROC curve, for sensitivity and specificity of the model versus using just strain on an echo? That's one question. And the other question is, does it have any difference in performance with AFib patients? Because we always have trouble getting good strain on AFib because of the heart rate variability. Thank you.
Yeah. Are you referring to the cardiac amyloidosis model for
Yes,
that one?
yes,
Yeah.
correct. Thank you.
So in our European Heart Journal, Jeremy, do you want to comment to that? You're the lead author.
Yes. So in our study, we compared the performance of the AI model to that of the IWT score, of which one of the parameters is strain. We know that GLS alone tends to have lower accuracy compared to the multi-parametric model. So rather than test it against a single parameter, we utilized a multi-parametric score that incorporated both apical sparing as well as the global strain into it, and found superior performance. And then your second question related to atrial fibrillation, those patients were not excluded from this study.
And we actually matched patients, controls and amyloid patients, for the presence of atrial fibrillation when we built the model, because of course the presence of atrial fibrillation would make the model more likely to think it was amyloid, so we had to be careful about that.
Very good.
Thank you very much. Really exciting technology. Going back to the HFpEF model, since it was built on patients with elevated filling pressure, does the detection change if the patient is diuresed and volume optimized, and does this have a role for ongoing management?
Thanks for that question. This is just one of the super exciting things we still need to look at.
I can attest to the fact that I've had patients that I get a positive HFpEF report at the end of the echo, and I see the patient in clinic, I initiate medical therapy, I repeat the echo 6 months later, and now it's negative. So it does, because all these parameters are changing on the echo, right? So your E to E prime is going to get better, your left atrium might get smaller, your IVC is going to get, so all those things that we typically look at as readers are changing. So that 4-chamber view is also changing, and as a consequence of that, I think it does change the output from the profiler.
I'm going to cheat and offer a comment, and it's a moot point because the first questioner already left, so I'm just going to respond to him. But when you're looking at it to administrators and trying to justify any increase in funding to find amyloid, you need to inform the hospital crew that the more amyloid they find, the more of a whole new stream of funding they're going to get by administering the new meds. I know in our institution we have this huge steel wall between hospital and university, and nothing is ever cross-matched between the two. But since we've been creating, because we're a big amyloid research center, since we've been creating literally dozens and dozens of new, $100,000 a year infusions for the hospital, they're just falling all over themselves to do whatever they want to support us.
Thank you for that comment.
And Steve was a part of this study, so he's been planted in the audience to ask great questions for us.
Thanks to the presenters for a terrific session. I was curious, in Dr. Jamal's real-world data, those 15 patients that you discovered over that 6-month period or so, just out of curiosity, have you looked with human versus AI as to how many would have been missed by humans and were picked up by AI?
Yeah, so that's something I'm very curious to see what we find. Like I said, so out of those 15, 10 were known cases. We knew that they had amyloidosis. They're already part of either our myeloma clinic or cardiac amyloid clinic for ATTR. Of the other 5, we wanted to look at all 5 of them. 1 had already passed away from leukemia. So then the other 4 have been referred, and I've initiated evaluations on these 4. So I am looking to see if I find amyloidosis in these 4 remaining patients, along with, so each quarter I'm going to do this, and I look forward to a year from now, hopefully, being able to come back and tell you, like these were echoes that we would not have reported as being suspicious, but, a certain percentage of these people ended up having amyloidosis that we discovered as a consequence of this screening process.
Yep. As you might imagine, our administrators are asking us what's the return on investment. Obviously, the previous speaker spoke to that, but the other issue is, how much better is it than humans, et cetera. So those are some of the curiosities we have in the real world data. So thanks.
For sure. Thank you.
Thank you. Any final questions? Very good. Well, thank you all for attending. I'm sure the speakers will be able to stick around for 5 more minutes to answer any other questions after the session. And a big thank you to our speakers for their talks today.